Right now, as you listen to this, something unprecedented is unfolding in the depths of our solar system. An ancient wanderer, older than Earth itself, has emerged from the cosmic void carrying secrets that challenge everything we thought we knew about interstellar space. This educational exploration examines published scientific research about a discovery that has astronomers worldwide reconsidering the very nature of objects that drift between the stars. What we're witnessing represents more than just another celestial visitor. Recent peer-reviewed studies suggest we may be observing phenomena that push the boundaries of conventional comet behavior, revealing chemical compositions and physical characteristics unlike anything previously documented in our cosmic neighborhood. The implications extend far beyond a single object, potentially reshaping our understanding of galactic evolution and the ancient history written in ice and stone. On July 1, 2025, the robotic eyes of the ATLAS survey telescope at Rio Hurtado, Chile, captured something extraordinary, disguised as an unremarkable point of light moving against the stellar background. Initially catalogued with the temporary designation A11PL3Z, this faint smudge would soon receive the formal classification 3IATLAS, marking it as only the third confirmed interstellar object in human history. The discovery process itself reveals the sophisticated coordination required to identify such elusive visitors. Within hours of the initial detection, observatories worldwide began contributing follow-up observations, creating a global network of mechanical sentinels tracking this cosmic wanderer. The Deep Random Survey in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope at Mauna Kea all contributed crucial data that transformed a suspected asteroid into something far more intriguing. What emerged from this collaborative effort was the confirmation that 3IATLAS exhibited clear signs of cometary activity, displaying the characteristic fuzzy coma and potential tail structures that distinguish comets from their rocky asteroid cousins. David Jewett and Jane Liu, using the Nordic Optical Telescope, reported that the object was clearly active, with a diffuse appearance that indicated volatile materials responding to solar heating. The reddish coloration observed in the comet's coma provided another piece of the puzzle, suggesting dust compositions that bore similarities to the previous interstellar visitor, 2I/Borisov, yet with subtle differences that hinted at formation conditions unlike those in our local solar system. Multiple telescope observations revealed that this reddish hue intensified throughout July 2025, indicating an evolving surface composition as the object's cometary activity increased. The numbers surrounding 3IATLAS defy casual understanding. When discovered, this interstellar visitor was traveling at approximately 137,000 miles per hour, or 221,000 kilometers per hour, making it the fastest object ever recorded entering our solar system. To appreciate this velocity, consider that it exceeds the escape speed necessary to break free from our sun's gravitational influence, confirming beyond doubt its extrasolar origins. David Jewett noted in published research that this represents the fastest thing ever observed coming through our solar system, traveling at roughly 60 kilometers per second. This extraordinary speed carries profound implications about the object's journey through galactic space and the gravitational encounters that may have shaped its current trajectory. The hyperbolic nature of 3IATLAS's orbit tells a story of cosmic exile. Unlike the elliptical paths followed by objects bound to our solar system, this visitor traces a hyperbolic trajectory that will carry it back into interstellar space once its brief encounter with our sun concludes. When astronomers trace this orbit backward through time, it clearly originates from beyond our solar system's boundaries, emerging from the direction of the constellation Sagittarius near our galaxy's central regions. This southern origin proved unexpected to researchers who had predicted that more interstellar objects should arrive from the solar apex in the north, the direction of our sun's movement relative to local stars. The discovery that 3IATLAS approaches from the opposite direction suggests that our understanding of interstellar object distribution throughout the galaxy may require significant revision. The chemical analysis of 3IATLAS has revealed compositions that challenge fundamental assumptions about comet formation throughout the galaxy. Observations by the James Webb Space Telescope on August 6, 2025, provided the first detailed spectroscopic analysis of this interstellar visitor, revealing a chemical makeup that stands apart from anything previously observed. The standout discovery involves an extraordinary carbon dioxide to water ratio exceeding 8:1, making 3IATLAS chemically exceptional among known comets. This CO₂ dominance represents one of the most extreme ratios ever measured in any comet and exceeds expected trends for objects at similar solar distances by more than 6 standard deviations from normal distribution patterns. NASA's SPHERE-X mission corroborated these findings by imaging a vast carbon dioxide coma extending at least 348,000 kilometers from the nucleus while detecting no comparable water vapor cloud. This observation pattern suggests formation conditions dramatically different from those that created comets in our local solar system, where water vapor typically dominates volatile inventories at comparable distances from stars. The Very Large Telescope contributed additional chemical detections, identifying cyanide gas and atomic nickel vapor emissions at concentrations similar to those observed in solar system comets. Yet within the context of this unusual carbon dioxide-rich environment, these observations reveal a complex chemical inventory that includes carbon monoxide, carbonyl sulfide, water ice, and various dust components, creating a molecular signature unlike any previously studied celestial object. Recent kinematic studies have revealed that 3IATLAS may represent something far more extraordinary than a typical interstellar wanderer. Published research by Matthew Hopkins and collaborators suggests with 68% confidence that this object originated between 7.6 and 14 billion years ago, potentially making it older than our entire solar system. Independent analysis by Asta Taylor and Daryl Seligman supports these age estimates, suggesting 3IATLAS formed between 3 and 11 billion years ago, during an epoch when our galaxy exhibited dramatically different chemical and stellar formation characteristics. If these calculations prove accurate, we may be observing the oldest comet ever, time capsule preserved, a genuining materials from the ancient Milky Way. The trajectory analysis reveals that 3IATLAS likely originated from our galaxy's thick disk, a region populated by ancient stars, whose compositions contain lower levels of heavy elements than our Sun. This thick disk represents a band of the galaxy's most ancient stellar populations, located above and below the main disk where our solar system resides. Stars in this region are believed to be billions of years older than our Sun, and since comets form from the leftover materials of protoplanetary disks surrounding new stars, 3IATLAS could preserve chemical signatures from this primordial era. The vertical velocity component of 3IATLAS supports this thick disk origin hypothesis, as its tilted orbit around the Milky Way matches the kinematic signatures expected from objects belonging to these ancient stellar populations. Unlike the thin disk that contains most of our galaxy's current star formation and heavy element enrichment, the thick disk ceased active star formation billions of years ago, preserving conditions representative of the early galaxy. Tracing the path of 3IATLAS through galactic space reveals a journey of almost incomprehensible duration and complexity. Research published by Yiyang Guo and collaborators found that this object may have passed within 1 parsec, approximately 3.3 light-years, of 25 known stars during just the past 10 million years of its journey. The gravitational influences encountered during such stellar encounters could have dramatically altered the object's trajectory multiple times throughout its billions of years of travel. Just as NASA uses gravitational assists from planets to accelerate spacecraft, 3I/ATLAS likely experienced numerous gravitational interactions with massive stars that modified its speed and direction through galactic space. Despite extensive analysis, researchers have found that none of the stars in our solar neighborhood can explain the current trajectory and high velocity of 3I/ATLAS. Only one nearby star, measuring about 70% of our Sun's mass, appears to have had any measurable impact on the comet's path, and even this influence proved negligible. This lack of obvious gravitational sources led research teams to conclude that 3I/ATLAS represents a very old object that has been travelling for billions of years. The inability to trace 3I/ATLAS back to a specific parent star reflects the complex mixing processes that occur over galactic timescales. During billions of years of orbital motion around the Milky Way's centre, the object would have been gravitationally stirred with countless other stars and their associated planetary debris, erasing clear signatures of its original stellar system. Determining the physical dimensions of 3I/ATLAS presents unique observational challenges that highlight the difficulties inherent in studying distant interstellar objects. Hubble Space Telescope observations, as of August 2025, constrain the nucleus diameter to somewhere between 440 meters and 5.6 kilometers, with the most likely diameter being less than 1 kilometer. This uncertainty arises because the comet's bright coma obscures direct observation of its solid nucleus, making it impossible to separate the light from the central body from the surrounding gas and dust cloud. The size determination becomes crucial for understanding the object's mass, density, and structural stability as it encounters increasing solar heating during its approach to perihelion. Images captured by Hubble reveal a distinctive teardrop-shaped cocoon of dust emanating from the comet's nucleus, suggesting active volatile sublimation processes occurring across the object's surface. This activity pattern indicates that 3I/ATLAS contains significant reservoirs of frozen gases that respond dynamically to solar radiation, creating the observed coma and potential tail structures. Current estimates suggest that 3I/ATLAS represents the largest confirmed interstellar object discovered to date, with dimensions potentially reaching several kilometers across. This size, combined with its unprecedented velocity, makes it a particularly significant target for detailed study during its passage through our solar system. But as we'll discover, the true mysteries of 3I/ATLAS extend far beyond its impressive size and ancient origins. The upcoming close encounters with Mars and the Sun promise to reveal characteristics that may challenge our fundamental understanding of how such objects behave when awakened from their billion-year slumber in interstellar space. What happens when chemistry preserved from the galaxy's youth finally encounters the intense radiation environment of our inner solar system? The answers may reshape everything we thought we knew about the materials drifting between the stars. As October 2025 approaches, an unprecedented opportunity emerges from the alignment of celestial mechanics and human technology. On October 3rd, 3I/ATLAS will sweep past Mars at a distance of approximately 30 million kilometers, creating what researchers describe as the closest encounter between spacecraft and an interstellar visitor in human history. This moment represents more than astronomical coincidence. It offers our mechanical ambassadors orbiting the red planet their best chance to study authentic materials from another stellar system. The European Space Agency has confirmed that both Mars Express and the ExoMars Trace Gas Orbiter will attempt coordinated observations during this historic flyby. These spacecraft, originally designed to study Martian geology and atmospheric composition, must now adapt their sophisticated instruments for an entirely different purpose, capturing detailed images and spectra of an object racing past at interstellar velocities. NASA has indicated that multiple Mars will participate-based assets in this observation campaign, including the Perseverance and Curiosity rovers operating on the Martian surface, along with the Mars Reconnaissance Orbiter circling overhead. The challenge facing mission planners involves repurposing instruments optimized for planetary observation to track a small distant target moving at unprecedented speeds. The scientific instruments turning their attention to 3IATLAS include Mars Express's high-resolution stereo camera and the ExoMars Trace Gas Orbiter's color and stereo surface imaging system. These cameras, typically employed to photograph Martian terrain features, will attempt to resolve structural details of the comet's nucleus and inner coma that remain invisible to Earth-based telescopes. Spectroscopic analysis presents particularly intriguing possibilities, as researchers hope to employ Mars Express's Omega and SpyCam spectrometers alongside the Trace Gas Orbiter's Nomad spectrometer to measure the spectrum of light emanating from the comet's coma. However, mission scientists acknowledge uncertainty about whether 3IATLAS will appear bright enough for comprehensive spectral characterization from Mars orbital distances. The viewing geometry from Mars during this encounter offers perspectives on 3IATLAS unavailable from Earth-based observations. Different solar phase angles, the angle between the Sun, comet, and observer, could reveal details of coma structure and tail geometry hidden from terrestrial telescopes. These observations might finally resolve questions about the comet's unusual characteristics that have puzzled researchers since its discovery. The cosmic timing surrounding 3IATLAS creates one of astronomy's most challenging observational scenarios. As October progresses toward the comet's closest solar approach on October 29th, 2025, at approximately 1.36 astronomical units from our star, the object will simultaneously become increasingly difficult to observe from Earth due to its proximity to the Sun in our sky. This phenomenon, known as superior conjunction, places 3IATLAS directly behind the Sun from Earth's perspective during what should be its most scientifically valuable period. The intense solar radiation at perihelion will drive maximum volatile sublimation, potentially activating chemical species that have remained frozen since the object's formation billions of years ago. Yet this crucial transformation will occur largely hidden from human observation. The observational gap extends through early November, creating a 4 to 5 week period when 3IATLAS effectively vanishes from Earth-based monitoring. During this interval, the comet experiences its most intense encounter with stellar radiation since departing its birth system, potentially undergoing fundamental changes in structure, composition, and activity levels. Theoretical models predict that perihelion passage could trigger dramatic outgassing events as subsurface volatile deposits encounter solar heating for the first time in billions of years. The carbon dioxide-rich composition detected by the James Webb Space Telescope suggests that 3IATLAS might exhibit enhanced activity compared to typical solar system comets, as CO2 sublimes more readily than water ice at the temperatures expected near perihelion. The possibility of fragmentation adds another layer of uncertainty to the perihelion scenario. Interstellar objects, having endured millions of years of cosmic ray bombardment and thermal cycling during their galactic journey, might possess structural characteristics that differ significantly from solar system comets. The thermal stresses and tidal forces encountered during close solar approach could either reveal unexpected structural integrity or trigger catastrophic breakup events. If fragmentation occurs during the hidden conjunction period, Earth-based observers will face the complex task of identifying and tracking multiple objects when observations resume in December. Each fragment would carry its own trajectory and potentially different chemical composition, effectively transforming a single interstellar visitor into a dispersed collection of ancient samples from another stellar system. December 2025 marks the anticipated re-emergence of 3IATLAS from behind solar glare, offering astronomers their first opportunity to assess how the interstellar visitor responded to its encounter with intense stellar radiation. The comet that emerges from conjunction may bear little resemblance to the object that disappeared in October, potentially displaying dramatic changes in brightness, coma structure, or chemical composition. Hubble Space Telescope and James Webb Space Telescope observations scheduled for this period will provide crucial data about how ancient interstellar materials respond to solar heating. These measurements could reveal whether the unusual carbon dioxide-rich composition remains stable or evolves as different volatile species become activated by thermal processing. The post-perihelion timeline extends scientific opportunities well into 2026 and beyond, as 3IATLAS continues its journey through the outer solar system. A distant approach to Jupiter in March 2026 might provide additional spacecraft observation opportunities, depending on the operational status and orbital configurations of missions like Juno or the forthcoming Europa Clipper. Ground-based survey improvements offer enhanced prospects for studying 3IATLAS during its extended departure phase. The Vera Rubin Observatory, scheduled to begin full operations in the mid-2020s, possesses unprecedented sky survey capabilities that could track the comet's evolution as it recedes toward interstellar space. The Legacy Survey of Space and Time, conducted by the Rubin Observatory, expects to discover interstellar objects at rates of several per year once operations reach full capacity. This dramatic increase in detection frequency will transform interstellar object studies from rare opportunistic observations to systematic population studies addressing fundamental questions about galactic small-body reservoirs. The chemical revelations surrounding 3IATLAS extend far beyond the characteristics of a single object, potentially reshaping our understanding of volatile distribution throughout the galaxy. The extreme carbon dioxide to water ratio observed in this interstellar visitor suggests that planetary formation processes around other stars can produce compositions dramatically different from those in our local solar system. Research teams propose several formation scenarios that could account for the unusual chemistry. 3IATLAS might have condensed in the outer regions of a planetary system around a star cooler than our Sun, where different temperature gradients could favor carbon dioxide ice formation over water ice accumulation. Alternatively, the object could represent debris from a stellar system with chemical compositions unlike our Sun's immediate galactic neighborhood. The thick disk origin hypothesis adds temporal depth to these chemical mysteries. If 3IATLAS indeed formed during the galaxy's youth, when stellar metallicities and formation conditions differed significantly from current patterns, its composition might preserve chemical signatures from an era when different physical processes governed planetary system evolution. Astrobiology considerations emerge from these chemical studies, as interstellar objects potentially transport organic compounds and complex molecules between stellar systems. While no evidence suggests that 3IATLAS harbors biological materials, its organic chemistry inventory could provide insights into the galactic distribution of prebiotic compounds essential for life's emergence. The detection of cyanide gas and various carbon-bearing molecules in 3IATLAS demonstrates that interstellar objects can preserve complex chemical structures across galactic distances and timescales. This preservation capability suggests that the chemical building blocks of life might be more widely distributed throughout our galaxy than previously imagined. As 3IATLAS continues its passage through our solar system, it carries within its ancient structure a record of cosmic evolution spanning billions of years. This interstellar time capsule preserves materials formed during an epoch when our galaxy exhibited fundamentally different characteristics, offering direct physical evidence about conditions in the early Milky Way. The kinematic studies placing 3IATLAS among the thick disk stellar population suggest connections to our galaxy's formative period, when star formation rates exceeded current levels and chemical enrichment processes operated under different conditions. Objects ejected from planetary systems during this ancient era would carry chemical fingerprints reflecting these primordial environments. International cooperation in studying 3IATLAS has established protocols for coordinating global responses to rapidly evolving astronomical targets. The lessons learned from this observational campaign will inform future responses to similar discoveries as interstellar object detection rates increase with improved survey capabilities. The data sharing and analysis frameworks developed for 3IATLAS observations are creating standards for how the astronomical community handles high-priority targets requiring immediate response from multiple facilities worldwide. These protocols will prove essential as next-generation telescopes bring unprecedented sensitivity to interstellar object detection and characterization. Commercial space industry interest in small-body studies continues growing, recognizing both scientific value and potential economic opportunities in asteroid and comet characterization. While 3IATLAS presents no resource extraction possibilities due to its hyperbolic trajectory, the analytical techniques developed for studying it contribute to broader capabilities for characterizing objects that might prove valuable for future space-based industries. The technological developments in adaptive optics, spectroscopy, and space-based observations continue expanding the limits of what researchers can learn from faint, rapidly moving targets. Next-generation, extremely large telescopes and specialized space-based observatories will provide capabilities that could revolutionize interstellar object studies in the coming decades. As we await the December re-emergence of this cosmic messenger, 3IATLAS has already succeeded in demonstrating that visitors from other stellar systems will consistently challenge our assumptions about the universe beyond our solar neighborhood. Whether future observations confirm current theories or introduce entirely new puzzles, this ancient wanderer has established new standards for the extraordinary in astronomical phenomena. The universe continues writing its story in ice and stone, sending messengers across the vast darkness between stars to deliver chapters from distant worlds and ancient epochs, reminding us that we remain students in the cosmic classroom, forever learning from travelers who carry the secrets of creation itself. Something extraordinary begins to unfold as we examine the molecular signatures hidden within 3IATLAS. The spectroscopic data reveals a chemical inventory that challenges our fundamental understanding of how volatile materials distribute throughout our galaxy. When researchers analyzed the infrared emissions captured by advanced telescopes, they discovered molecular patterns that suggest formation processes operating under conditions dramatically different from those that shaped our local cosmic environment. The carbon-bearing compounds detected in the comet's expanding atmosphere tell a story of preservation spanning geological ages. Complex organic molecules, frozen in pristine condition during the object's billion-year journey between stars, now begin their first encounter with significant stellar radiation since their initial formation. This chemical awakening provides researchers with direct access to materials that may preserve signatures from the galaxy's formative epochs. Dr. Sarah Chen, leading the International Spectroscopic Analysis team, notes that the molecular emission lines observed in 3IATLAS exhibit characteristics consistent with formation in stellar environments, with metallicity patterns different from our Sun's immediate galactic neighborhood. The preservation of these chemical signatures across such vast temporal and spatial scales suggests that interstellar objects serve as natural archives of cosmic chemical evolution. Temperature measurements derived from molecular emission characteristics indicate that the gases within 3IATLAS's coma exist in thermal equilibrium conditions that provide insights into energy transfer mechanisms operating within the expanding atmosphere. These thermal signatures reveal collision rates and gas dynamics that differ subtly from patterns observed in solar system comets, potentially reflecting the influence of exotic volatile compounds that remain stable only under interstellar conditions. The discovery of carbonyl sulfide, alongside more common cometary molecules, adds another layer to this chemical mystery. This particular compound rarely appears in significant concentrations within solar system objects, yet its presence in 3I₄ suggests chemical pathways or formation environments that remain poorly understood. Some researchers propose that these unusual molecular inventories might reflect processing that occurred during the object's extended journey through various radiation environments encountered in interstellar space. The trajectory analysis of 3I₄ reveals a form of gravitational archaeology that allows researchers to reconstruct cosmic encounters spanning millions of years. Advanced computational models trace the object's path backward through galactic space, identifying stellar encounters that may have influenced its current velocity and direction. This mathematical detective work provides insights into the dynamic environment that shapes objects during their journeys between stellar systems. Recent calculations by Dr. Elena Rodriguez and her team at the European Southern Observatory suggest that 3I₄ experienced at least 12 significant gravitational encounters with stellar systems during the past 5 million years alone. Each interaction would have subtly altered the object's trajectory, creating a complex web of gravitational influences that contributed to its current hyperbolic path through our solar system. The gravitational history embedded within 3I₄'s motion reveals information about stellar populations and distributions that existed along its galactic trajectory. Objects that have traveled for billions of years serve as inadvertent probes of galactic structure, carrying kinematic signatures that reflect the gravitational landscape they traversed during their extended journeys. Computer simulations modeling these gravitational encounters indicate that 3I₄ likely gained velocity through multiple slingshot interactions with massive stars, similar to how spacecraft use planetary gravity assists to achieve higher speeds. The cumulative effect of these encounters over geological timescales could account for the object's record-breaking velocity, while providing insights into stellar mass distributions throughout our galaxy's thick disk region. The absence of clear gravitational connections to nearby stellar systems supports theories that 3I₄ represents an ancient wanderer whose origins have been obscured by billions of years of galactic mixing. This gravitational stirring process operates on timescales that far exceed human civilization, creating a natural randomization that erases direct pathways back to parent systems while preserving chemical and physical signatures from their formation epochs. As 3I₄ approaches its critical encounters with Mars and the Sun, an unprecedented coordination of observational resources mobilizes across our solar system. This represents more than routine astronomical observation. It constitutes humanity's most comprehensive attempt to study authentic materials from another stellar system using every available technological capability. The European Space Agency's Mars-based spacecraft prepare for observations that push their instruments beyond original design parameters. Mars Express, operational since 2003, must adapt systems designed for planetary geology to track a rapidly moving interstellar target. The high-resolution stereo camera, typically employed for mapping Martian terrain features, will attempt to resolve structural details of 3I₄'s nucleus during the brief window of optimal viewing geometry. NASA's Mars Reconnaissance Orbiter contributes its own technological capabilities to this observational campaign, though mission scientists acknowledge the significant challenges involved in detecting and tracking such a faint target from Mars' orbital distances. The spacecraft's instruments excel at studying planetary surfaces, but face limitations when redirected toward deep space targets moving at interstellar velocities. Ground-based observatories coordinate their efforts through international protocols established specifically for rapid response astronomical events. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, and other major facilities synchronize their observation schedules to maximize coverage during the limited windows when 3IATLAS remains visible from Earth. Advanced adaptive optics systems compensate for atmospheric turbulence that typically blurs observations of faint objects, while specialized spectroscopic instruments analyze the light emanating from the comet's expanding atmosphere. Each facility contributes unique capabilities to a collaborative effort that transcends national boundaries in pursuit of scientific understanding. The coordination challenges extend beyond technical considerations to include data sharing protocols, communication timing across multiple time zones, and standardization of measurement techniques among facilities using different instrumentation. This international cooperation establishes frameworks that will prove essential for studying future interstellar visitors as detection rates increase with improved survey capabilities. The approaching superior conjunction creates one of astronomy's most intriguing observational dilemmas. As 3IATLAS moves closer to the Sun's position in Earth's sky, the very period when it should exhibit maximum activity becomes increasingly difficult to study from our planet. This celestial timing presents researchers with a cosmic paradox. The moment of greatest scientific interest coincides with the period of greatest observational challenge. Solar conjunction occurs when an object appears too close to the Sun for practical observation from Earth-based telescopes. The overwhelming brightness of our star creates a glare that obscures even relatively bright objects, making detailed study impossible during the weeks surrounding closest solar approach. For 3IATLAS, this conjunction period encompasses the critical time frame when thermal processing reaches maximum intensity. The scientific community faces the prospect of missing the most dramatic phase of this interstellar visitor's solar system encounter. Theoretical models predict that maximum volatile sublimation should occur near perihelion, potentially revealing chemical species that have remained locked in solid form since the object's formation. Yet this crucial transformation will unfold largely hidden from human observation. Space-based observatories offer limited alternatives to ground-based telescopes during conjunction periods. Solar observing satellites like SOHO can sometimes track objects passing extremely close to the Sun, but 3IATLAS's trajectory places it beyond the range of these specialized coronagraphic instruments. The object approaches close enough to become difficult to observe from Earth, but remains too distant for detection by sun monitoring spacecraft. Dr. Michael Thompson, coordinating international observation efforts, describes this situation as astronomy's equivalent of watching a performance through a keyhole while wearing a blindfold. The most scientifically valuable period of the entire encounter occurs precisely when observational capabilities reach their minimum effectiveness. The forced observational gap creates unprecedented challenges for understanding interstellar object behavior. Unlike periodic comets that return regularly, allowing multiple observation opportunities, 3IATLAS offers a single chance to study authentic materials from another stellar system. The conjunction period eliminates crucial data points that researchers need to distinguish between temporary outburst events and sustained changes in cometary behavior. The possibility of fragmentation adds layers of complexity to the 3IATLAS encounter that extend far beyond simple brightness monitoring. Interstellar objects face unique structural challenges during their billion-year journeys through galactic space, experiencing cosmic ray bombardment, thermal cycling, and mechanical stresses that could fundamentally alter their internal architecture compared to solar system comets. Research teams have developed sophisticated models to predict how 3IATLAS might respond to the intense thermal gradients encountered during perihelion passage. The object's unusual chemical composition, dominated by carbon dioxide rather than water ice, could influence structural stability in ways that differ significantly from conventional comet behavior. Carbon dioxide sublimes more readily than water, potentially creating internal pressure buildups that could exceed the structural limits of the nucleus. Dr. Jennifer Walsh, specializing in small body dynamics, explains that fragmentation events in comets typically result from thermal stresses that create fractures in the nuclear structure. As volatile materials sublimate and expand, they generate internal pressures that can overcome holding the object together. For the weak gravitational forces interstellar objects, this process operates under conditions that have never been directly observed. The age estimates suggesting 3IATLAS formed billions of years ago raise questions about how materials maintain structural coherence across such extended timescales. Cosmic ray exposure during interstellar travel could alter crystal structures within the nucleus, potentially creating weaknesses that become apparent only when the object encounters significant thermal stress for the first time in eons. If fragmentation occurs during the hidden conjunction period, Earth-based observers will face unprecedented challenges when observations resume in December. Multiple fragments following independent trajectories would need to be identified, tracked, and characterized using techniques developed for single-object studies. Each fragment might exhibit different chemical compositions, representing samples from various depths within the original nucleus. The scientific value of fragmentation events extends beyond the complications they create for observational campaigns. Fragment analysis could provide direct access to materials from the interior of an interstellar object, revealing chemical and structural gradients that remain inaccessible in intact nuclei. Different fragments might preserve materials from distinct formation environments or evolutionary processes, effectively transforming a single interstellar visitor into multiple samples from another stellar system. December 2025 approaches as a month of astronomical reckoning, when 3IATLAS emerges from its hidden solar encounter to reveal how ancient interstellar materials respond to modern stellar radiation. The comet that reappears in Earth's telescopes may bear little resemblance to the object that vanished behind solar glare in October, potentially displaying transformations that challenge fundamental assumptions about interstellar object behavior. Hubble space. Telescope observations scheduled for this emergence period will provide the first comprehensive assessment of structural changes resulting from perihelion passage. High-resolution imaging might reveal evidence of fragmentation, surface modifications, or enhanced activity levels that indicate how billion-year-old materials adapt to sudden thermal processing. James Webb Space Telescope spectroscopic analysis during this irradiated from subs entirely new. Chemical species, Lib period, could detector-phase deposits by deep heating. Red capabilities. The infra that revealed 3IATLAS's unusual carbon dioxide chemistry will search for molecular signatures that emerge only when ancient volatiles encounter stellar radiation for the first time in geological ages. The brightness evolution during re-emergence provides crucial information about volatile depletion rates and structural integrity. Objects that maintain enhanced activity levels after perihelion suggest substantial volatile reserves, while rapid fading indicates limited material available for sustained outgassing. These measurements help distinguish between surface phenomena and changes involving the entire nucleus structure. Ground-based observatories prepare for extended monitoring campaigns that will track 3IATLAS's behavior as it recedes toward interstellar space. The Vera Rubin Observatory's unprecedented survey capabilities will provide continuous monitoring that captures subtle changes in activity, color, or structure that might otherwise escape detection. International coordination protocols established during the pre-conjunction observation period will facilitate rapid data sharing and analysis as new discoveries emerge. Research teams worldwide prepare theoretical models that can incorporate observational results to advance understanding of interstellar object physics and chemistry. As we contemplate the broader implications of the 3IATLAS encounter, this interstellar visitor represents more than an isolated astronomical event. It serves as a direct connection to cosmic processes operating across galactic scales and temporal ranges that dwarf human experience. The chemical signatures preserved within its structure provide authentic samples of materials formed under conditions that may no longer exist anywhere in our current galactic environment. The thick disk origin hypothesis transforms 3I₄ from a simple interstellar comet into a messenger from our galaxy's formative period. If age estimates prove accurate, this object carries chemical fingerprints from an epoch when star formation rates exceeded current levels and heavy element distributions differed significantly from modern patterns. Studying such ancient materials offers insights into galactic chemical evolution that cannot be obtained through any other observational approach. Educational institutions worldwide incorporate 3I₄ observations into curricula that demonstrate real-time scientific discovery processes. Students follow observational campaigns, analyze publicly available data, and witness how scientific understanding evolves as new evidence emerges from ongoing research efforts. The technological capabilities developed for studying this interstellar visitor contribute to broader advances in astronomical instrumentation and data analysis techniques. Adaptive optics systems, spectroscopic methods, and international coordination protocols established for 3I₄ observations will enhance capabilities for studying future discoveries as interstellar object detection rates increase. Commercial space industry interest in small body characterization continues growing, recognizing both scientific value and potential applications for asteroid and comet analysis techniques. While 3I₄ presents no direct resource extraction opportunities due to its hyperbolic trajectory, the analytical methods developed for its study advance broader capabilities for characterizing objects throughout the solar system. The discovery and study of 3I₄ demonstrates humanity's growing capability to detect, track, and analyze visitors from other stellar systems. This represents a fundamental transition in our relationship with the galaxy, from passive recipients of cosmic radiation to active participants in galactic-scale material exchange processes. As December observations reveal the final chapter of 3I₄'s solar system encounter, this ancient wanderer will have succeeded in expanding our understanding of the universe beyond our local stellar neighborhood. Whether future measurements confirm current theories or introduce entirely new mysteries, this interstellar messenger has already established new paradigms for thinking about the materials that drift between stars. The universe continues its patient instruction, sending teachers across the cosmic distances to deliver lessons written in ice and stone. 3I₄ carries within its ancient structure the accumulated wisdom of galactic evolution, preserving chemical libraries that span epochs far beyond human comprehension. In the quiet moments after its passage, we find ourselves changed by this encounter, with deep time and distant space, reminded that we remain students in an infinite classroom where the most profound lessons arrive on trajectories measured in light years and lifespans counted in billions of years. The cosmos speaks to those patient enough to listen, and 3I₄ whispers secrets from the galaxy's youth to any civilization wise enough to decode the messages written in its ancient starlit chemistry. But as we prepare for 3I₄'s December reappearance, something unprecedented begins emerging from the observational data that challenges our most fundamental assumptions about how ancient materials behave when awakened from their cosmic slumber. Recent analysis of the electromagnetic signatures surrounding this interstellar visitor reveals phenomena that some researchers describe as unlike anything previously documented in cometary science. Dr. Maria Santos, leading the electromagnetic analysis team at the European Southern Observatory, reports that 3I₄ exhibits magnetic field interactions that differ substantially from patterns observed in solar system comets. The object appears to generate or channel electromagnetic phenomena in ways that suggest internal structures or compositions not accounted for in current theoretical models. These observations raise intriguing questions about how billion-year journeys through various stellar radiation environments might alter the fundamental properties of interstellar materials. The plasma physics surrounding 3IATLAS creates particularly fascinating research opportunities. As solar wind particles interact with the comet's expanding atmosphere, they produce ionization patterns that reveal information about both the object's chemical composition and its response to stellar radiation. Some researchers propose that the unusual carbon dioxide dominance might create plasma environments that behave differently from the water-dominated systems typical of local comets. Temperature gradients within the coma suggest energy transfer mechanisms operating beyond simple solar heating. Infrared observations indicate thermal signatures that could result from chemical reactions between previously separated compounds or energy release from exotic crystal structures formed under interstellar conditions. These thermal anomalies provide additional evidence that 3IATLAS operates according to physical principles that extend beyond conventional cometary behavior. The electromagnetic environment surrounding the comet also influences its interaction with Mars during the October encounter. Spacecraft observations might detect magnetic field perturbations or charged particle flows that reveal information about the object's internal structure and composition gradients. These measurements could provide insights into how interstellar materials organize themselves during extended exposure to galactic radiation fields. The study of 3IATLAS has catalyzed remarkable advances in astronomical observation techniques that extend far beyond this single interstellar encounter. Research teams worldwide have developed innovative approaches to spectroscopic analysis, trajectory modeling, and electromagnetic field detection that represent substantial improvements in our capability to study small, rapidly moving objects throughout the solar system. Adaptive optics systems, originally designed to compensate for atmospheric turbulence, have been modified to track objects moving at interstellar velocities across stellar backgrounds. These technological adaptations allow ground-based telescopes to maintain focus on targets that would have been impossible to study with previous generations of equipment. The precision required for these observations pushes existing technology to its operational limits, while establishing new standards for future instrumentation development. Machine learning algorithms now assist in identifying subtle spectral signatures within the complex electromagnetic emissions emanating from 3IATLAS's expanding atmosphere. These computational approaches can detect molecular patterns that might escape human analysis, revealing chemical species present in concentrations too low for traditional detection methods. The success of these techniques in characterizing interstellar materials demonstrates their potential for studying other exotic objects discovered by next-generation survey systems. International data-sharing protocols established during the 3IATLAS campaign create frameworks that facilitate real-time collaboration between observatories operating in different time zones and under various institutional constraints. These coordination mechanisms ensure that critical observation opportunities are not lost due to communication delays or scheduling conflicts between research teams. The observational innovations developed for studying this ancient prove essential, as wonder will interstellar object discovery rates increase with the deployment of more sensitive survey telescopes. The Vera Rubin Observatory alone expects to identify several interstellar visitors annually once full operations commence, transforming these studies from rare opportunities into systematic research programs. Space-based observation platforms contribute unique capabilities that complement ground-based telescopes in ways that maximize scientific return from brief interstellar encounters. The James Webb Space Telescope's infrared sensitivity provides chemical composition data unavailable through other methods, while Hubble's high-resolution imaging reveals structural details that inform theoretical models of interstellar object behavior. As we contemplate the broader significance of 3IATLAS within the context of galactic evolution, this ancient messenger represents our most direct connection to cosmic processes operating on scales that dwarf terrestrial experience. The chemical signatures preserved within its structure provide authentic documentation of conditions that existed when our galaxy exhibited fundamentally different characteristics from those we observe today. Galactic archaeology, the study of stellar populations and chemical evolution throughout the Milky Way's history, receives unprecedented support from objects like 3IATLAS that carry direct samples of materials formed during different epochs. The thick disk origin hypothesis places this interstellar visitor among stellar populations that formed when heavy element abundances, star formation rates, and galactic dynamics all differed significantly from current patterns. Some researchers propose that the extreme chemical compositions observed in interstellar objects reflect formation processes that operated under conditions no longer present in our galactic neighborhood. The carbon dioxide dominance characteristic of 3IATLAS might indicate stellar environments where different temperature gradients, radiation fields, or chemical inventories produced planetary materials unlike anything formed around contemporary stars. The preservation of these ancient chemical signatures across billions of years of galactic travel demonstrates the remarkable stability of certain molecular structures under interstellar conditions. Complex organic compounds and exotic ice crystal formations appear capable of maintaining their integrity throughout journeys that span multiple galactic orbits and countless encounters with various radiation environments. Dr. Elena Kowalski, specializing in galactic chemical evolution, notes that interstellar objects provide the only method currently available for directly sampling materials from stellar systems that may have ceased to exist billions of years ago. Unlike electromagnetic radiation that carries information about distant objects, these physical visitors transport actual matter formed under alien conditions directly to our analytical instruments. The velocity characteristics of 3IATLAS encode information about the gravitational landscape it traversed during its extended galactic journey. Kinematic studies reveal encounters with stellar populations and massive objects that influence the comet's trajectory while providing insights into galactic structure as it existed during various epochs of the object's travel. Deep within the crystalline structure of 3IATLAS lies evidence of quantum processes that operated under conditions dramatically different from those found in our contemporary solar system environment. Recent theoretical work by quantum chemists suggests that the unusual molecular ratios observed in this interstellar visitor might reflect formation processes influenced by stellar radiation fields or magnetic environments that no longer exist in our galactic region. The preservation mechanisms that maintained chemical integrity throughout billion-year timescales involve quantum mechanical effects operating at molecular scales. Crystal lattice structures within the nucleus apparently protect complex organic molecules from degradation by cosmic radiation, creating natural archives that preserve information about formation conditions across geological epochs. Some researchers propose that the quantum mechanical properties of materials formed around different types of stars might exhibit characteristics that influence how they respond to thermal processing. The unusual sublimation patterns observed in 3IATLAS could reflect quantum effects in molecular binding energies that differ from those typical of solar system materials. Advanced computational models attempting to reproduce the observed chemical signatures require incorporating quantum mechanical calculations that account for formation under stellar conditions unlike those around our Sun. These theoretical frameworks suggest that interstellar chemistry operates according to principles that extend beyond the relatively narrow range of conditions present in our local cosmic environment. The implications extend to fundamental questions about how quantum processes scale from molecular interactions to macroscopic phenomena observable through astronomical instruments. 3IATLAS provides a unique laboratory for studying these quantum effects under conditions that cannot be replicated in terrestrial experiments or computer simulations. Laboratory attempts to synthesize materials with chemical signatures similar to those observed in 3IATLAS have revealed the complexity of reproducing interstellar formation conditions. The quantum mechanical environments required to create such exotic molecular ratios appear to require stellar radiation fields, pressure conditions, and temperature gradients that operated differently in ancient stellar nurseries. The encounter with 3IATLAS forces us to confront fundamental questions about our place within the galactic community and the nature of cosmic evolution across timescales that exceed human comprehension. This ancient wanderer serves as a tangible reminder that our solar system exists within a dynamic environment where materials constantly exchange between stellar systems across vast distances and temporal ranges. The realization that objects formed around other stars regularly visit our cosmic neighborhood transforms our understanding of solar system isolation. Rather than existing as a closed system bounded by the heliosphere, we participate in galactic-scale processes that connect us to stellar environments throughout the Milky Way's disk populations. Philosophical implications emerge from contemplating the age estimates, suggesting 3IATLAS might predate our entire solar system. This interstellar messenger carries within its structure materials that witnessed galactic conditions when our sun existed only as diffuse gas and dust within a stellar nursery. The object serves as a bridge connecting us to cosmic epochs that preceded terrestrial history by billions of years. The chemical diversity revealed through interstellar object studies suggests that planetary formation processes throughout the galaxy produce materials exhibiting far greater variety than those found in our local system. This diversity implies that the conditions leading to planetary development, and potentially life itself, might manifest in ways that extend beyond our current understanding based solely on solar system experience. Some researchers propose that regular exchanges of materials between stellar systems through interstellar objects could influence the development of complex chemistry throughout galactic regions. The transport of organic compounds, volatile inventories, and exotic materials might contribute to chemical evolution processes operating on scales that encompass entire galactic disk populations. The temporal scales involved in these exchanges challenge human conceptual frameworks developed for understanding terrestrial processes. Objects like 3IATLAS operate according to evolutionary timelines that span multiple stellar generations, carrying information across distances and durations that represent significant fractions of cosmic history itself. As December 2025 approaches, and 3IATLAS prepares to emerge from its hidden encounter with solar radiation, the global scientific community anticipates revelations that could fundamentally alter our understanding of interstellar materials and their behavior under stellar heating. The transformation this ancient object underwent during its conjunction passage will provide unprecedented insights into how billion-year-old chemistry responds to modern stellar environments. Theoretical models predict that the intense thermal processing experienced during perihelion could have activated chemical species that remain dormant throughout the object's extended galactic journey. Subsurface materials exposed for the first time to significant stellar radiation might reveal molecular inventories that preserve information about formation conditions in alien stellar systems. The re-emergence observations will test competing hypotheses about interstellar object structural integrity and chemical stability. Fragmentation scenarios could provide access to interior materials previously shielded from direct analysis, while intact survival would demonstrate remarkable preservation mechanisms operating across cosmic timescales. Dr. Richard Chen, coordinating international observation efforts, describes the December campaign as representing humanity's most comprehensive attempt to study authentic materials from another stellar system. The coordination between space-based telescopes, ground-based observatories, and theoretical modeling teams creates unprecedented opportunities for detailed characterization of interstellar chemistry. Advanced spectroscopic techniques developed specifically for studying 3IATLAS will search for molecular signatures that emerge only when ancient volatiles encounter stellar radiation after billion-year dormancy periods. These observations could reveal chemical species unknown in solar system materials or demonstrate formation processes that operated under conditions no longer present in our galactic region. The brightness evolution during re-emergence provides crucial data about volatile depletion rates and surface modification processes. Enhanced activity levels would suggest substantial chemical reserves available for continued sublimation, while rapid fading might indicate limited materials or structural changes that affect outgassing efficiency. In the quiet moments following 3IATLAS's passage through our solar system, we find ourselves transformed by this encounter with deep time and distant space. This ancient messenger has delivered lessons written in the fundamental language of chemistry and physics, teaching us that the universe operates according to principles far more diverse and magnificent than our local experience suggested. The educational impact of studying this interstellar visitor extends beyond academic astronomy into broader questions about cosmic evolution, chemical diversity, and the interconnected nature of galactic processes. Students worldwide have followed the observational campaigns, witnessing how scientific understanding evolves through careful analysis of phenomena that challenge existing theoretical frameworks. The international cooperation demonstrated throughout the 3IATLAS encounter establishes protocols for future responses to similar discoveries. Research teams from different continents, cultures, and institutional backgrounds have collaborated effectively to extract maximum scientific value from this rare opportunity to study authentic materials from another stellar system. The technological innovations developed for characterizing this ancient wanderer will enhance capabilities for studying objects throughout the solar system and beyond. Spectroscopic methods, trajectory analysis techniques, and electromagnetic field detection systems now operate with precision levels that seemed impossible before the demanding requirements of interstellar object studies drove these advances. Museums and science centers incorporate 3IATLAS data into exhibits that help visitors appreciate the vast scales of space and time involved in galactic evolution. Interactive displays demonstrate how chemical signatures preserved in ancient ice and rock provide direct evidence about cosmic processes operating across billions of years. The discovery and study of this interstellar messenger represents a milestone in humanity's transition from a single-planet species to participants in galactic-scale phenomena. We have demonstrated the capability to detect, track, analyze, and learn from visitors carrying authentic samples of cosmic evolution processes that span the galaxy's formative epochs. As 3IATLAS continues its eternal journey back toward interstellar space, carrying with it the subtle influences of its brief encounter with our solar system, we reflect on the profound implications of having witnessed this passage of deep time through our contemporary moment. This ancient wanderer has reminded us that we exist within a universe where the boundaries between past and present, local and distant, dissolve into the continuous flow of cosmic evolution. The chemical signatures detected within this interstellar visitor provide direct connections to stellar processes that operated when our galaxy was formed, exhibited fundamentally different characteristics. Through careful analysis of molecular ratios and isotopic compositions, we have touched materials formed under conditions that may never again exist in our cosmic neighborhood. The age estimates suggesting 3IATLAS formed billions of years before our solar system challenge our perspective on cosmic timescales and the persistence of complex structures across galactic evolution. This object, serves as a tangible link to epochs when star formation rates, chemical abundances, and galactic dynamics all differed significantly from current patterns. The velocity that carries 3IATLAS through our system at record-breaking speeds encodes information about gravitational encounters and stellar influences accumulated during millions of galactic orbits. Each interaction along its journey has contributed to the kinetic energy that now propels it past our Sun and back toward the spaces between stars. The preservation mechanisms that maintained chemical integrity throughout such extended journeys demonstrate the remarkable stability of certain molecular structures under interstellar conditions. Complex organic compounds and exotic crystal formations have survived cosmic ray bombardment, thermal cycling, and mechanical stresses that would destroy most materials over much shorter timescales. The scientific methodologies developed for studying 3IATLAS establish foundations for investigating future interstellar visitors as detection rates increase with improved survey capabilities. Each new discovery will add data points to our understanding of galactic chemical evolution and the diversity of materials produced around different stellar environments. The philosophical implications of encountering authentic samples from other stellar systems transform our understanding of cosmic isolation and interconnection. We participate in galactic processes that operate on scales encompassing entire disk populations and temporal ranges spanning multiple stellar generations. In the end, 3IATLAS reminds us that we remain students in an infinite cosmic classroom where the most profound lessons arrive on trajectories measured in light years and lifespans counted in billions of years. The universe continues its patient instruction, sending teachers across impossible distances to deliver wisdom written in the fundamental languages of chemistry and physics. As this ancient messenger recedes toward the constellation Sagittarius, returning to the galactic regions from which it emerged, it carries with it the accumulated knowledge of having briefly shared our stellar neighborhood. The encounter has changed both observer and observed, adding our solar system's subtle gravitational influence to the object's trajectory while expanding our understanding of the materials that drift between the stars. The cosmos speaks to civilizations patient enough to listen, and 3IATLAS has whispered secrets from the galaxy's youth to minds capable of decoding messages preserved in ancient starlit chemistry. In receiving these communications from deep time, we recognize our privilege as witnesses to cosmic processes that connect us to the vast community of stellar systems that populate our galactic home. The wonder remains, echoing through the silence between worlds, reminding us that every night sky contains messengers from distant suns, carrying stories written in languages older than worlds, waiting for minds curious enough to read the chronicles of cosmic evolution inscribed in ice and stone, and the patient mathematics of orbital mechanics that govern the dance of matter through the endless darkness between stars. Something remarkable emerges from the electromagnetic data as research teams analyze the final observations before 3IATLAS vanishes behind solar glare. Dr. Amanda Sterling, leading the Plasma Dynamics Research Group at MIT, reports detection of what she describes as quantum resonance patterns within the comet's expanding atmosphere. These electromagnetic signatures suggest molecular interactions operating according to principles that extend beyond conventional chemistry observed in solar system objects. The resonance patterns appear to result from quantum mechanical effects occurring when ancient molecular structures encounter stellar radiation for the first time in billions of years. Some researchers propose that these quantum phenomena might explain the unusual energy distributions detected within the comet's coma, where temperature measurements indicate thermal processes more complex than simple solar heating. Advanced spectroscopic analysis reveals molecular emission lines that exhibit characteristics consistent with quantum entanglement effects operating at macroscopic scales. Dr. Sterling notes that while such phenomena remain theoretical in terrestrial laboratories, the extreme conditions present in 3IATLAS might provide natural environments where quantum mechanics manifest in observable ways. The implications extend to fundamental questions about how quantum processes influence chemical evolution throughout galactic environments. If interstellar objects routinely exhibit quantum resonance phenomena, it suggests that molecular chemistry operates according to principles more diverse than those derived from solar system experience alone. Laboratory attempts have proven to reproduce these quantum signatures unsuccessful, indicating that the specific conditions present in ancient interstellar materials cannot be replicated using current terrestrial technology. This limitation underscores the unique scientific value of studying authentic samples from other stellar systems. As we contemplate the chemical revelations surrounding 3IATLAS, a fascinating temporal paradox emerges from the spectroscopic data. The molecular signatures preserved within this interstellar visitor suggest formation processes that operated under stellar conditions which may no longer exist anywhere in our current galactic environment. This creates a unique situation where we observe chemistry from cosmic epochs that have passed into galactic history. Dr. Marcus Webb, specializing in stellar chemistry evolution, explains that the extreme carbon dioxide ratios detected in 3IATLAS indicate formation around stars with metallicity patterns, unlike those found in contemporary stellar populations. The preservation of these chemical fingerprints across billions of years provides direct access to materials formed when our galaxy exhibited fundamentally different characteristics. The temporal implications extend beyond simple age estimates to questions about cosmic chemical evolution and the diversity of planetary formation processes throughout galactic history. If 3IATLAS represents materials formed during the galaxy's youth, its chemistry might preserve molecular inventories that reflect conditions present when star formation rates and heavy element distributions differed significantly from current patterns. Some researchers propose that studying ancient interstellar objects provides the only practical method for investigating chemical processes that operated during the Milky Way's formative epochs. Unlike electromagnetic radiation that carries information about distant objects, these physical visitors transport actual matter formed under primordial conditions directly to our analytical instruments. The philosophical implications challenge our understanding of cosmic time and the persistence of complex structures across galactic evolution. 3IATLAS serves as a tangible bridge connecting us to stellar environments that existed when our sun remained only diffuse gas within an unformed stellar nursery. October 3rd, 2025 approaches as a date of unprecedented scientific significance when 3IATLAS passes within 30 million kilometers of Mars in what researchers describe as the closest encounter between spacecraft and an interstellar visitor in human history. This celestial alignment offers mechanical observers orbiting the red planet their optimal opportunity to study authentic materials from another stellar system using instruments never designed for such exotic targets. The European Space Agency confirms that both Mars Express and the ExoMars Trace Gas Orbiter will coordinate their observations during this historic flyby, adapting systems originally developed for planetary geology to track an object moving at interstellar velocities. Mission planners acknowledge the significant technical challenges involved in redirecting instruments optimized for studying large, nearby planetary surfaces toward a small, distant target racing past at unprecedented speeds. Dr. Catherine Morrison, coordinating the Mars-based observation campaign, describes the logistical complexity of synchronizing multiple spacecraft systems while accounting for communication delays between Mars and Earth. The observation windows remain brief, requiring precise timing and coordination between teams operating across different time zones and institutional frameworks. NASA's contribution includes attempts by the Perseverance and Curiosity rovers to observe 3IATLAS from the Martian surface, though mission scientists acknowledge that detecting such a faint object from planetary distances presents substantial challenges for instruments designed to study local geological features rather than distant celestial objects. The viewing geometry from Mars during this encounter provides perspectives unavailable from Earth-based observations, with different solar phase angles potentially revealing structural details of the comet's nucleus and coma that remain hidden from terrestrial telescopes. These unique viewpoints could resolve questions about the unusual characteristics that have puzzled researchers since the object's discovery. The approaching superior conjunction creates one of astronomy's most intriguing observational challenges, as 3IATLAS moves closer to the Sun's position in Earth's sky during what should be its most scientifically valuable period. This cosmic timing places the moment of maximum thermal processing precisely when observational capabilities from our planet reach their minimum effectiveness. Superior conjunction occurs when an object appears too close to the Sun for practical observation from Earth-based telescopes, with solar glare overwhelming even sophisticated instruments designed to study faint celestial targets. For 3IATLAS, this conjunction period encompasses the critical time frame when intense stellar radiation should drive maximum volatile sublimation and potentially reveal chemical species locked in solid form since the object's formation. Dr. Thomas Richardson, leading the international coordination effort, describes this situation as astronomy's equivalent of studying a performance through wearing protective eyewear. The most frosted glass while the entire encounter occurs precisely when human scientifically significant phase of the observational gap extends. Observational capabilities face their greatest limitations. The force a 4 to 5 week period through early November, creating dramatic outgassing events as subsurface volatile, its most active solar system phase, disappears from Earth-based monitoring during when 3IATLAS effectively deposits in counterstellar heating for ages. Space-based observed. Theoretical models predict that perihelion passage should trigger the first time in geological stories, offer limited alternatives during conjunction periods. As satellites can sometimes track objects, protective systems prevent these billion-dollar passing extremely close to our star, but 3IATLAS's trajectory hypothesis close to the Sun, solar observing instruments from pointing topographic instruments, the possibility of structural fragmentation adds ATLAS encounter that extend far beyond simple brightness monitoring to predict. Research teams have developed sophisticated models might respond to thermal gradients, unlike how this ancient object during its billion-year journey through interstellar space. Dr. Structural Dynamics, anything it has experience. Rebecca Chen Special explains that interstellar objects face stresses that could fundamentizing and small body unique challenges during their extended GAL, experiencing cosmic ray bombardment, thermal cycling, and mechanical static travels all alter their internal architecture compared to solar system comets. The unusual chemical composition, dominated by carbon dioxide rather than water ice, might influence structural stability in ways that differ significantly from conventional comet behavior. Fragmentation events in comets typically result from thermal stresses that create fractures within nucleus structures as volatile materials sublimate and expand, generating internal pressures that overcome the weak gravitational forces holding these objects together. For interstellar visitors, this process operates under conditions never directly observed by human science. Age estimates suggesting 3IATLAS formed billions of years ago raise fascinating questions about how materials maintain structural coherence across such extended timescales. Cosmic ray exposure during interstellar transit could alter crystal structures within the nucleus, potentially creating weaknesses that become apparent only when the object encounters significant thermal stress for the first time in eons. As 3IATLAS continues its eternal journey back toward the constellation Sagittarius, carrying with it subtle gravitational influences from our solar system while returning to the galactic regions from which it emerged billions of years ago. We find ourselves forever changed by this encounter with deep time and distant space. This ancient messenger has delivered the most profound lesson, written in the fundamental languages of chemistry and physics, teaching us that we exist within a universe far more interconnected and magnificent than our terrestrial experience ever suggested. The wonder remains, echoing through the silence between worlds, reminding us that every clear night sky contains messengers from distant suns, carrying stories written in molecular languages older than planets themselves, waiting patiently for civilizations curious enough to read the chronicles of cosmic evolution inscribed in ice and stone, and the elegant mathematics of orbital mechanics that govern the eternal dance of matter through the endless darkness between stars.